Welcome you all to this Cryo-EM course. Last class we discussed about if there is a multiple sine or cosine curve, how they overlap with each other, and then how it is increasing their amplitude. That means your resultant wave will have a either higher amplitude than actual wave, or it is reduced that amplitude of that wave. So, how they are overlapping with each other, that is more important, and same time we also discuss about that okay, if that is possible, there is a 2, 3 or multiple waves are coming together and they are giving different kind of architecture. So, that is also possible if we have a different types of periodic function, we can split them into very simple sine and cosine curve. So, that last example I gave you to this one. So, if you recall last class, what we use, this is a complicated periodic function and that oscillates in a different way, but you can see this is basically the periodic function it is going. And now if you want to simplify these things, that okay, how many waves are there, so that is called the decomposition of this complicated wave, or we can say that that is a Fourier decomposition. We are not going to discuss about the details about the mathematical details about the Fourier decomposition, but this is a very basic idea how we can consider that Fourier decomposition, and what is the basic formula of that Fourier decomposition if you want to apply. That basically help us when we will talk about our Cryo-EM 3D reconstruction or structure determination, because most of the time when you will get a 2D image, we have to take this 2D image and we have to move to the Fourier space, and then we have to do most of the 3D reconstruction. That is the reason it is better to know little bit about this Fourier decomposition also. So, last class also I discussed that okay, if I have only one choice, I will basically select this kind of wave to represent this particular complex wave function. So, it has a constant amplitude and will now if I have a second option, so I will prefer to use a cosine curve, and here you can see this will be the amplitude and this will be the cos kx. Then if I have a third option, then definitely I will select a wave something like that, which will go up and down like this, and amplitude will be B1 and sine kx. Then next choice, you can see that here the frequency is increasing. This one we can say only one wave is there. Here you can see there is a 2 complete wavelength is there. So, if the frequency is changing, and that is why we are selecting that A2 cos 2 kx. And then same thing is possible for that next wave. If I can select, here you can see that frequency is changing, that ups and down oscillation is more, and then we are selecting that okay, we can add this 5 waves and probably we can get this kind of complicated periodic function. Now, if I have a more choices, I can select this wave where this wave is oscillating 3 times, and here we are selecting, that is the wave we are selecting here. You can see that frequency is changing, again here it is oscillating also 3 times, and we are selecting this one. Now, if we want to write a general formula from this one, what we can do, so best way to do it, that we have a function f of x, then what kind of wave we selected? We selected a wave a0 by 2 at the beginning, and then there are many waves are coming. So, something like that. Okay, first we selected a1 cos kx, then b1 sin kx plus again A2 cos 2kx plus B2 sin 2kx plus again A3 cos 3kx plus B3 sin 3kx and so on. So, now if we can simplify these things, and it will keep going on. If there is a very complicated function, we will just show little bit about the step function, because you can see that step function also it is a straight line, and but that also we can represent using a sine or cosine curve. And so, here you can see there is a multiple waves. So, some are cosine curve or sine curve, and we are adding them together, and we are representing any complicated function. So, if we just rearrange these things, what will happen? So, it will come like that: A1 cos kx plus A2 cos 2 kx plus A3 cos 3 kx plus A4 cos 4 kx and so on. Same thing is possible for the other one, that is B sin kx plus B2 sin 2 kx, B3 sin 3 kx and B4 sin 4 kx. You can see that frequency is changing and amplitude is also changing. Now, from this one, what we can draw a simplify this equation. So, something like that A0 by plus 2 by, we can make it that m equals to 1 to infinity Am, that is the amplitude. So, here we can put it m means 1 to infinity. So, we can add waves where amplitude will be A1, A2, A3, A4, A5 like that until infinity, and then cos k mx plus same thing is true for m1 infinity Bm sin k mx. So, you can see that entire these things we simplified and we represented in this way. So, where there will be a same amplitude, so we will use this constant, and then we have a cosine function and sine function to represent any wave. Now, if we have to determine that what will be the amplitude Am, generally this amplitude will determine by this one 0 to infinite. So, f of x cos m k x dx and Bm 2 by infinity. So, 0 to infinity f of x sin m k x dx. So, at this moment, for our purposes, if we do not remember these two things, it is still okay, there is not too much problem, but this is the basic concept that okay, when we have any kind of wave function, and if it is a periodic function, we can use that this sine and cosine wave and represent that wave. So, why it is required? If you remember, when I was drawing the ray diagram for TEM images, there are multiple waves are coming and converging in one particular point, and that is giving you the first diffraction spot. If you try to analyze that diffraction spot, it will be not a single wave, it is a multiple wave coming and converged in one particular point, and there it will be a different type of wave function, all are merged together and giving that spot. And further, if you go from that one, you will get that image. That is the reason when you will get that spot, and if you want to decompose that spot, that how many waves are there, we can decompose this wave in this way. And that is the reason it is telling that Fourier decomposition of any periodic function. Now, if we go here, from that formula, if you just remember that formula, I will go to the next page. So, here if we just write that formula again, f of x, what is there, a 0 by 2, and then this is summation, this is infinity, m equals to 1 a m cos k m x plus summation m equals to 1, then b m sin k m x. Now, if we just replace these things, that a 0 by 2, what we are getting, infinite m equals to 1, you will get a m cos 2 pi m x by lambda. We are bringing lambda here because this is the spatial frequency. The spatial frequency we are replacing by lambda. So, here the angular part is there, lambda is there, which is help us to explain that wave properly. So, here you can see this will be b m, then sin k will be replaced by 2 pi by lambda, 2 pi by lambda m x. Okay. And then if we have this one, now if you look, if I just make a table, what we have, as I told that m will vary, right. So, sorry, this, let me write that m properly, m equals to 1 here. So, if we just vary that m, so m I am telling that frequency is 1, 2, 3, 4, that number it is changing, right. So, here if we just make a table, that m x and that sign, right, what do we get? We will get it something like 1 when m equals to 1, this wave it will oscillate, this wave it will oscillate only once within that. So, when it is oscillate this, it will go 0 to lambda and angle will be 0 to 2 pi. Okay. Then what is our, we are just changing the frequency. If you remember that when there is a complicated wave function, we are just changing, adding the sine and cosine curve, but their frequency was changing. So, in this case when we are using 2, m equals to 2, what is happening here? This either this in the sine wave, or it will go as a cosine wave. It will start from here and end. So, you can see that it is oscillating twice, right, but it is going 1 lambda to 0 to 1 lambda, 0 to 1 lambda, but this angle if you just consider, it will just switch 0 to 4 pi. So, you can see if we just go, it is just changing the frequency, how many numbers are there. So, again if you just consider 3, it will go 0 to 6 pi, something like that, and it will keep going on and will keep adding different types of wave together. So, here there is another wave function is there in my PPT. I will just show that one and then we will go to the next step. Here in this particular wave you can see there is a very complicated wave function. It is there, it is going up and then there is a 3 bump and then again it is going to minus x, it is going all the way up, again it is following this periodic path and then it is going up. So, here this is one cycle. Now, if we want to split that wave and make it a simple wave, what you can do, first you can select a wave, it is like, it is the first harmonic, then the second, then the third one. In all the cases you can see only the frequency it is changing and definitely its amplitude is also changing and we are adding all this wave. So, we will keep going on with this and if we add that, finally we will adding up this from first wave to all this 6 wave, we will get the resultant wave is this one. Now, when we are trying to plot those things, we cannot see wave when we will record some TEM images or any images, right. We can see the contrast difference, we can see the amplitude, basically we are plotting amplitude squares. So, here whenever we are looking at the wave, so as I mentioned previously in last class also, that if we are standing in front of a sea and the different types of waves are coming, if the waves amplitude is very high, it will just suppress most of the slow moving wave where amplitude is not that big. So, here the first wave from this one we are using this one and then gradually we are going this one, and all the cases you can see the frequency is increasing, simultaneously your amplitude is also decreasing. When we are looking at that very big wave in front of the sea, that is basically the amplitude. So, when we are plotting anything, even if we are recording the diffraction pattern or our images, what we are recording? We are recording that amplitude, that amplitude squares we are plotting. So, here if we just measure this one, this will be the amplitude here, this will be the amplitude here of individual wave. So, if we want to represent this wave, what we can do? We can see these amplitudes are here. So, it is something like that, those waves are moving, we are taking those waves and then rotate this entire wave on top of that the plane, and we are looking at those amplitudes and we are plotting those amplitudes. So, whenever we will talk about the diffraction pattern, we are talking about all these wave, how it is plotting there. Now, we will come to another simple form that we have to discuss these things, that how we are going to plot those sum wave. That as I mentioned, that most of the time when we are recording a image, we are not recording the sine wave or cosine wave, we are plotting or recording that amplitude or amplitude square. Here we are, you do not have to follow all this instruction here, you just follow that graph. If you do not follow this one, that is also fine. Here what you can see, this is a sine wave, right, this sine wave going like this, or this is a cosine curve basically, and this is a sine curve if you just consider. So, now I want to plot those amplitude. When you will plot this amplitude, we will plot this amplitude squares here in this diagram. So, this will be the amplitude in both the directions. So, wave is propagating the x minus x and plus x direction. So, it will be the spatial frequency k, and when we will plot, this wave will be presented in both the side x and minus x and plus x, both the sides in equally, and only we are plotting this amplitude. So, here we are representing this amplitude. The other one, and what will be the position of this one? Based on their frequency, this position will vary. So, here the frequency is 1. So, we are plotting it and one position. Okay. The same thing here also, but here you can see this wave is in a different direction. In this y axis it is going x axis. So, if I just use a different color, it will be easy to understand. So, I will just erase this particular part. So, here I will use a blue color here. So, this wave propagates in this direction, and same way here this, and here also you can see both the sides they are in the same position, and if we just consider this will be the one frequency. So, we are just using the spatial frequency to plot that. Now, here this one you can see is a one wavelength completed, but they are in a two different position. It is just switch. So, when we are trying to plot, we will plot this amplitude square. Now, when you look at those wave, different kind of complicated wave function, we can see some dots, bright spot in our images. That is basically we are talking about the diffraction pattern, and where it is going to form that bright dot. So, we are plotting that amplitude square, and that is basically recording. So, that position, it is depending on the frequency of that particular wave where this position will be. If I go to the next slide, it will be much more clear. Here you can see there are different types of waves, and based on the frequency we are trying to plot that. This one we already discussed, that when there is a fixed amplitude and infinite frequency. So, we want to plot that one, it will come here at the 0 position. So, first wave, whenever we are trying to describe any wave, we are using this straight line with a fixed amplitude. So, this is the function that f of x equals to a, and that we can plot it at the 0 position. Okay. Now, there is a different types of waves, we can see it. Here you can see one wave. This is a cosine curve, and it is going, the frequency is 1. If we just look at that, so we are getting that at frequency 1, and both are in same side, there is no opposite phase. So, both are in the same position. So, we are plotting this one here and here. As I told that, when this wave propagates it, so similar information is there in minus direction and plus direction also, and that is why we are representing this entire thing, that both the spot will be available in plus k and minus k both. Now, we are coming to the second one. The second wave, here you can see this is the same cosine curve. This curve is oscillating like this. So, here when this is oscillating, they completed here, we can continue this one like this. So, when it is oscillating, in both the cases you can see this is the frequency is 3 here. It is 3 times oscillated, ups and down, ups and down, ups and down 3 times. So, if frequency is changing, amplitude is almost same, we can consider. Now, when we are plotting this particular function, as I mentioned, this function will stay in both the information, that amplitude square, we have to plot it in plus x and minus x, both the direction. Again, we are plotting these things here, where we are using minus 3k0 and plus 3k0, and we are plotting these amplitude squares here. So, whenever we will look at any image, we cannot see this sine curve or cosine curve like that. What we can see, even we cannot see this kind of arrow also. What we can see some kind of very bright dotted spot, something like that. If I just use a different color, you will see something, this bright spot. And this bright spot, how brighter it will be, it is depending on the amplitude. And here, that what position will get that spot, that is also depending the frequency of that wave, and the center spot as we draw it here, this is the central part, will be a bright spot will be available here. Okay. So, now there is a one more function. If this is the straight line and one wave, this cosine wave, it is going in this direction, and then you can see this is so here this is the up, and then so this will be the major function, and then both the side you will get at minus k0, because here frequency again 1. So, you will get a 2 bright spot at minus k0 and plus k0. Okay. So, this is how we are, because initially we started with Fourier decomposition, and we started with a Fourier decomposition, and then we have a multiple sine and cosine curve. We also understand when we are getting a bright spot, what is the meaning of that bright spot, or how do we decompose that bright spot using the sine and cosine curve. That is called the Fourier decomposition. Now, when we have a multiple sine wave or cosine wave which we have the amplitude there. So, we are plotting this amplitude square in our diagram or in our images. So, amplitude squares, that is representing as a white spot when we are taking those images, and in electron microscope those things we are recording when we have the microscope. I already discussed about the back focal plane. Back focal plane is the first plane where we will get the images. What kind of images we will get it? We will get the images of the diffraction pattern or diffraction pattern of our sample. So, back focal plane is the first imaging plane in our electron microscope, where we are going to record the diffraction pattern, and diffraction pattern means these are the diffraction pattern. If we just same function, that sine, that there are sine function, that we are transforming this to and plotting it as a amplitude square. So, again there is another wave. If you look at here, you have another wave, and here this one is the function is that f of x equals to a sine k0 x. So, here frequency is 1, and we are plotting that one, but you can see if we just start from this point 1 and this particular part and this particular part, they are opposite with each other, and that we are plotting here. Okay. This is called the transformation, how there is a multiple sine wave is there, how we are transforming those things to another form and recording those things as an image. So, that is called the diffraction pattern, and from the diffraction pattern we will get the image. So, there is a relationship. If we have a sample here, so the electron beam will come here. So, if we just consider that this is the objective lens, and then we are getting some kind of images here, we are getting the diffraction pattern here. So, when we are getting those dots, it is depending on the frequency. If frequency is 1, so dots will be very close to each other, and dots should come in both the sides in plus x minus x, that way. And now, when the frequency is much more higher, you will get dots far away from your central position. Then this is basically we are getting the diffraction pattern, we can tell diffraction pattern, and now if we continue this one, we will get an image. What we discuss this here, we are getting the diffraction pattern. Diffraction pattern basically we already discussed that this is the Fourier transform, right? Fourier transform of this, whatever object it is there, and we are getting some kind of scattered and unscattered electron beam, they converge, and that is a complicated sine cosine curve, they merge together, and finally we are plotting that amplitude. That is, we are constantly talking about that Fourier decomposition. And then if we just go further, we are getting that image. Okay. So, image, if we just do the inverse Fourier transform, we will get this diffraction pattern or this diffraction pattern, if we do the Fourier transform, we will get that image. So, here there is a relationship between the Fourier object and image and their diffraction pattern and the Fourier transform. This relationship part we are going to discuss in the next class. So, I thank you all for your attention. So, in next class we will discuss more about the diffraction pattern, and from this diffraction pattern how we are getting the images. This will help us during our image reconstruction classes. Thank you.